Hey folks, welcome back to Advent of Code in F#, and I have another summary for you for day 20. Day 20 is pulse propagation, where we have to propagate a lot of pulses through a system of AND and flip-flop gates. So a quick recap, we had like a wire scheme that says like this is connected to this. No, this is the one, yeah. This is connected to this is connected to this. So it's basically a dot graph. It's basically a graph notation. And we have different types of nodes. Some are conjunction modules, which like AND their inputs and remember all their inputs. And the other ones are flip-flops, which invert the signal, I guess. No, it flips when it receives a low pulse and then it sends a high pulse. It's stuff like that. So maybe it is a flip-flop. Probably it is a flip-flop. Otherwise, they wouldn't have called it a flip-flop. But yeah, so it's a little wire scheme, and we have to run signals through this scheme and see how many pulses that get sent, I think, for part one. Or we have to count all low and all high pulses and like calculate the product of those two. So part one was a simple simulation exercise. I just implemented it just as stated. So I defined my pulses, I defined my modules, I defined my different module types, which are flip-flops and conjunction. Let's take a quick look at how I defined those, because I'm using syntax I have not used, I think, this year, which are these record type thingies with the extra bars in there. This little thing is called an anonymous type. So this is a type, but it does not have a name. It's there. And I use it sometimes. I don't always use it, but I use it if I have like a union type and I want to say off some other type. Before this existed, you had to type an explicit type name here and you had to create a new type. But now with these anonymous things, you can just inline it. So, okay, a broadcaster is a module and it can contain data, and this is like the broadcaster data type, but it has no explicit name. It's just like implicitly or anonymously created here, this type. So that's what these weird syntax is. Or not weird, but you don't see it that often. So yeah, I define my broadcaster's special module type, and then I have my flip-flops and my conjunction. And as you can see, every module has an output. Now that I look at it, or now that I implemented the solution this way, I'm not really happy about having the ID and the outputs like inside each of these different anonymous types. This means that for every time we need to grab an ID out of one of these, or if we have a module somewhere in our algorithm and we want to grab the module ID, I need to do a pattern match, because the ID is like not shared state in a super class somewhere. So I don't know if I would model this the same a second at a time, but this is how I did it, so this is how it stays. I'm not in the business of cleaning up Advent of Code code. There's too little time in the day. So yeah, this is my type definition. As always, I have an accompanying module for the type if I have some interesting logic, and this is what I was saying. If I want to extract an ID or a list of outputs from modules, if you define them like this, like they all have their special cases with their own custom types, and they share ID fields and output fields, you have to pattern match, and that's why I wrote these two helper functions to extract outputs and IDs of these different cases. Parsing wise, there's not a lot going on. As always, I don't use parser combinator libraries or regexes because I suck at them. I just do string mangling, which is what you see here. And the only interesting part I wanted to take some pause and discuss is I'm doing a two-phase parsing. One phase I just parse line by line, and in the other phase I think I connect inputs to outputs, something like that. So this states like module A has two outputs, but we need to connect the graph somehow, and connecting the graph is something I do in a second pass of the parsing algorithm. So yeah, this is what you see here, the connect modules. That takes the modules list, which is like a line by line parse of what we saw here, and it returns a modules list. So it does something to the modules, but what it does is what you can see here. It takes a look at, okay, what modules output or this input, what modules does this output? So I just grab the outputs, and then I link the inputs. That was it, yeah. So every module also has inputs, or some modules have inputs, broadcast does not have, for example, but then I just, if this is correct, I only need the link for the conjunction type. So that's interesting. Not every module type needs this, but the conjunction definitely needs this, because it needs to remind a lot of, it has no single input, it has several inputs, so it needs to know where it's coming from, those pulses, so it can keep track of the different inputs. Yeah, so this is the second phase of the parsing, where I connect my conjunction modules using a simple lookup and hooking them into the inputs. So that's all I do for parsing. And then I literally have some pulse propagations. So this is a type that says, okay, from this module to that other module, we're sending a high or a low pulse. So this is what a propagation is. And then I see state, so probably I'm going to use a fold in 2 seconds, but this is keeping track of everything while I'm running the algorithm, or while I'm running the simulation. It keeps track of a lookup table containing all modules. It has a queue of all the pulses, because if you take a look at the exercise, there's a very distinct order in which pulses need to be sent. It's not depth first, it's breadth first, it's something like that. I don't really remember, because it's been a couple of days, but it's a very specific order in which we have to send these pulses. That's why this queue is there, so we can do a last in, first out kind of thing. First in, first out, first in, first out for a queue. And we just keep track of all the propagated pulses, because we need to know how many lows and highs we sent. So that's what you see here in the propagated list. And then we have our algorithm, which is not a fold, it's just a big ass. It's a very big function. It's recursive even. And yeah, it's the same you see in breadth first, stuff like that. So we take a look at the queue. If the queue of work is empty, we're done, and we just return the state. Otherwise, we have a propagation we need to take care of. So we take a look at where does this go. So which destination module, we look it up, and then we take a look at what kind of module we have here. And there's a try find. That it was an interesting observation I had. The example doesn't have it, but my input did. There was like a module that only had outputs. It was not defined anywhere. There was no line defining the module. And that becomes very interesting for part 2. But for part 1, that broke my algorithm and my brain a bit. This is why I just hacked in this try find to kind of short circuit that. So there are modules in there that have no line definitions, and that's a little hack I put in here to work for that case. And otherwise, we just pattern match on the type of module, and we do whatever we have to do for that module. So broadcaster is just that gets like the pulse from the button. I didn't have to model it that way, but I like doing it. So I think you even need to count the pulse now that I see this. So probably you have to do it, or otherwise you'll have an off by whatever, off by a couple of button clicks. So yeah, I pattern match and I just update the state accordingly, which is most of the time putting new signals in the queue, first in, first out, and remembering every pulse we have propagated so we can count the number of lows and highs at the end. For flip-flops, it's doing the same thing. And it needs to flip them when we need to pulse or forward a pulse, stuff like that. And that needs a lot of more work to output its pulse. And conjunction is the same, which is like something like an AND gate. So there's a bit of logic for that as well. Yeah, and there's like an initial state we need to build. So we have no propagated signals. We have a single pulse we want to propagate, which is going from the button to the broadcaster, and it's a low pulse. And that's the initial state. And then we needed to, I don't remember, we needed to press the button a lot of times for part 1. I think it was 1,000. Yeah. So I just call that function 1,000 times. So I sent 1,000 pulses through my wire scheme. And then I just count the number of high and low pulses, which is really easy if you keep track of every pulse. And that was part 1, which was pretty cool. A cool simulation exercise, or at least that's how I solved it. And then I take a look at part 2. And that was insane. What was the problem description again? Oh yeah, there's one. So the one module that did not have a definition, it was only an output module. It was Rx. I think that has a specific term in the wire scheme world, but I'm not an expert. But yeah, there was this module that only had an output, or only was output 2, it was not defined, and we needed to see how many button presses we need to get like the first low pulse sent to that specific module. And that's it. And if I remember correctly, that thing was not even in the example, so we had little to go on except our own input here. And I ran it for a while using the simulation for part 1, and it took a while and nothing happened. No pulses were being sent. And as you can see, the answer here is a pretty big number. That's a lot of button presses. So, but I did not know that at the time, of course. So that was a bit mind-numbing. And I let my algorithm run, had a think on it, didn't figure it out. And then again, I went for a hint on the subreddit, the solutions megathread. And people were posting graph visualizations of their input, which was interesting. So I did it as well. I wrote a snippet of code to render our input as a graph. And if you know the dot file format of the graph viz tool, it's not really hard. You just have to define like your nodes and your edges like with a little arrow syntax. Maybe I have my dot file here somewhere. Yeah, so this is dot syntax. It's a really easy way to specify graphs. You just state like, oh, it's a graph. There's some special nodes that have a special color, so it's nicer on the eyes if you visualize them. And then you have my edges and my nodes. So this is an edge NL or node NL that connects to all these other nodes. So it's really, it almost maps identically to the input we have. So it's like a little wink to Graphis today. And if you render it, I don't know if I can show it. Not in my IDE, it seems. So let me open that SVG file up in a browser. Yeah, let's open it with Edge, sure. So as you can see, it's a biggish graph. And my node is my broadcaster right there, and the end node is Rx, so it has no outgoing edges. So it's a really big graph, and Rx was not getting fired. But if you take another look at this graph, you see that Rx only has one input. So there's only one thing that sends pulses to NS. Interesting. And if you take a look at that NS, you'll see that it's a conjunction. So this will only fire a low pulse if it has like, I don't remember, but if it has like pulses from its 4 inputs. So we have RV, VP, DC, and CQ. And those all have to fire their pulse at the same time in order for NS to forward the pulse. So you can make the problem a bit smaller if you take a look at these 4 inputs for that conjunction module. And if you calculate like the number of presses you need to have those 4 modules fire, you can just calculate the lowest common multiple, and that would be the button press where NS would forward its pulse, so where Rx would receive its first low pulse. So this was a tricky day for me. I definitely needed this help and this hint to take a look at the graph. But once I saw this graph and yeah, it made sense, and you can figure out, okay. But this is a tricky one because you really needed to take a look at the input, or at your specific input even, not the example. So it's a different flavor of algorithm or puzzles. It's not my favorite, but in the end, I learned about Graphis and the dot files and the graph visualization thing. So I learned a lot, and I think that's the goal of Advent of Code. So all in all, nice puzzle. Won't do it again, but a nice puzzle. So that's Advent of Code day 20 down. I hope you learned something, and hope to see you again next time. Bye-bye.